Flight 12 carries the key to cutting moon missions by 60%. Ship 39 deploys 6 Raptor 3 engines, the world's most powerful engines at 280 tons of thrust each, 25% lighter than Raptor 2, with 350 seconds of specific impulse. What does this power upgrade actually mean for getting to the moon? Experts predict lunar missions requiring 10 to 15 refueling flights with V2 could drop to just 4 to 6 flights with Raptor 3. Can SpaceX really prove this revolutionary reduction on Flight 12? Let's dive right in. SpaceX's recent road closure notice told us something big was moving to Massey's. Production to Massey's, midnight to 4 a.m. When SpaceX blocks the road at those hours, it usually means Booster 19 or Ship 39 is rolling out. But what actually appeared was a 2-ring barrel test section with a can crusher interface, destined for B8.3 sitting at the test site. Why does a test tank matter when we're talking about making history? Because every weld, every pressurization cycle, every structural proof on these test articles directly validates what Ship 39 and Booster 19 will face during Flight 12. The data flowing from Massey's right now is literally clearing the path for late January's launch. Ship 39 represents the most significant structural evolution Starship has ever seen. SpaceX completely redesigned how they build the nose cone, the section experiencing the most brutal aerodynamic forces and re-entry heating. The old V2 approach used multiple small steel gores assembled into short conical rings, stacked together with circumferential welds running horizontally around the structure. The problem? Those horizontal weld lines sit perpendicular to the main stress direction, creating weak points exactly where loads concentrate during ascent and engine burns. One compromised weld during max Q could mean catastrophic failure. V3 flips the entire construction method. SpaceX now uses long, straight steel panels forming the nose cone with primarily vertical welds. This isn't just about aesthetics. Vertical welds run parallel to dominant stress paths, allowing forces to distribute evenly across the structure instead of concentrating at weld intersections. The surface becomes smoother, loads transfer more efficiently, and structural margins increase dramatically. It's the kind of understated engineering change that doesn't make headlines, but fundamentally determines whether Ship 39 survives to orbit or breaks apart trying. And reaching orbit is exactly what Ship 39 needs to prove. Because beneath that redesigned nose cone sits the real revolution: 6 Raptor 3 engines. The world's most powerful full-flow stage combustion engines, each producing 280 tons of thrust at sea level. But raw power alone doesn't explain why this matters for the moon. Raptor 3 achieves specific impulse around 350 seconds, while cutting engine weight by 25% compared to Raptor 2. What does that efficiency gain unlock? The math is staggering. Current orbital refueling plans with Raptor 2 require 10 to 15 tanker flights to fully fuel a Starship HLS for lunar missions. Each tanker launch costs time, propellant, and operational complexity. With Raptor 3's improved efficiency and higher propellant delivery capacity, experts estimate missions drop to just 4 to 6 tanker flights. That's not incremental improvement, that's transforming lunar logistics from barely feasible to operationally practical. Can 6 engines really deliver that kind of mission profile change? Flight 12's data will answer definitively, but Raptor 3 brings more than numbers. These engines solve chronic reliability issues that plagued earlier versions: leaks, engine fires, inconsistent relight behavior in vacuum. For orbital refueling, where tankers must dock precisely with depots and transfer thousands of tons of cryogenic propellant in space, engine reliability isn't optional. One failed relight during rendezvous could mean losing the entire tanker. Raptor 3's multiple reliable vacuum relights and improved safety margins during docking operations directly enable the refueling architecture NASA's betting on for Artemis. The mission profile matters here. Starship HLS doesn't just fly to the moon. It orbits Earth, receives propellant from multiple tankers, burns for lunar transfer, enters lunar orbit, lands on the surface, takes off again, returns to lunar orbit, burns back to Earth, and re-enters. Every phase demands engine performance. Raptor 2 couldn't guarantee. Flight 12 proves whether Raptor 3 can handle that complete cycle. Now Booster 19 enters the equation. The first super heavy V3 ever built. The most visible change? 3 grid fins instead of 4, arranged with 2 fins close together at 90 degrees and a third opposite at 180 degrees. Removing a fin sounds like cutting safety margins, doesn't it? SpaceX claims control actually improves because each remaining fin is over 50% larger and weighs around 3 tons, providing greater authority during the steeper, hotter re-entry V3 boosters will experience. The fin placement matters just as much as size. They're mounted lower, around the methane tank section, with actuation mechanisms hidden inside the tank where they're protected from re-entry plasma. This positioning gives better leverage for controlling the booster's orientation during descent while reducing exposure to thermal damage. But does 3-fin control actually outperform 4-fin systems under real flight conditions? Nobody knows yet, which is exactly why Flight 12 will target a controlled splashdown instead of attempting a tower catch. SpaceX needs clean data from that re-entry. They need to see how those 3 fins handle hypersonic flow, how quickly they can correct attitude deviations, whether control authority remains sufficient during the high-G pull-up maneuver just before landing. Attempting a catch without that validation would be reckless, even for SpaceX's aggressive timeline. One upgrade Booster 19 will definitely demonstrate is the permanently attached hot staging ring, that massive crown sitting atop Super Heavy. Previously, this ring would separate and fall into the ocean after stage separation, requiring recovery boats, reinstallation teams, and 1 to 2 hours of integration work before the next flight. Fixing it permanently eliminates recovery operations entirely and cuts turnaround time. Does saving 2 hours per flight really matter? When you're planning dozens of Starship launches to establish a lunar base, those hours compound into weeks of schedule compression. But the biggest unknown on Flight 12 isn't the vehicles themselves, it's Launchpad 2. This facility represents SpaceX's bet on everything they've learned from 11 previous flights. The new flame trench with integrated water-cooled diverter has been tested repeatedly over recent months. Those dramatic water blasts visible from miles away. Why such extensive testing for a flame trench? Because Pad 2 needs to survive the full Starship V3 launch cadence, potentially weekly launches generating forces that destroyed sections of Pad 1. The OLM evolution tells the durability story. Gone is the old 6-leg structure. Pad 2 features a thicker, water-cooled steel deck built to handle higher loads and resist thermal damage from repeated Raptor 3 exhaust. Smaller, more compact booster quick disconnects with tighter hoods and better sealing cut propellant loading time, shaving precious minutes from the countdown sequence. When you're launching frequently, every minute of pad occupation matters. Then there's the tower upgrade that's easy to miss, but critical for future operations. Shorter chopsticks. The new robotic arms no longer extend far beyond the OLM, reducing inertia and aerodynamic drag. This allows faster movement, quicker response, and dramatically better precision during catch attempts. Why does speed matter for catching? During Starship's landing sequence, the vehicle performs a belly flop re-entry, flips vertical in the final moments, and hovers briefly while the tower moves in for the catch. The aft flaps near the tail pass through the chopsticks gap first. If the arms close too slowly, those flaps remain suspended between them, risking collision or complete catch failure. Pad 2's chopsticks also feature more powerful actuators. When Starship settles into catch position near the payload bay hardpoints, the chopsticks must close within seconds. The old system couldn't guarantee that speed consistently. The new actuators can, which matters enormously when you're planning daily Starship operations, where every landing must work flawlessly. Ship 39 won't be caught on Flight 12, but the pad systems proving they're ready for that future changes everything. Beyond Starbase, Massey's site received critical upgrades after the Ship 36 explosion in June 2025. SpaceX installed a massive truss structure around the static fire test stand, a tall lattice framework extending toward the payload section with integrated ship quick disconnects and crisscross steel bracing. This structure transforms how technicians access Starship during testing. Previously, routine maintenance, sensor installation, and engine inspections required slow, complex crane operations. Now technicians move directly onto platforms surrounding the vehicle, working at height without constant crane dependency. That speeds up testing cycles and reduces strain on launch site resources as SpaceX pushes toward higher test cadence for Block 3 vehicles. Flight 12 isn't just another test. It's SpaceX proving they've solved the moon equation. 6 Raptor 3 engines cutting refueling missions from 15 flights down to 6. Vertical weld construction ensuring Ship 39 survives forces that would tear apart earlier designs. 3 oversized grid fins providing better control than 4 smaller ones ever could. A permanently attached hot staging ring saving 2 hours per launch that compounds into weeks across dozens of missions. And Pad 2 standing ready to support the weekly launch cadence that makes all of this possible. Every upgrade on display during Flight 12 exists for one purpose: transforming lunar missions from barely achievable to operationally routine. When Ship 39 fires those Raptor 3 engines and Booster 19 descends under 3-fin control, we're not watching incremental progress. We're watching SpaceX validate the architecture that puts boots on the moon and eventually establishes a permanent human presence there. Late January could mark the moment when Elon's 2026 lunar timeline shifts from ambitious promise to engineering reality. The data from this flight will either confirm SpaceX cracked the code or send them back to redesign critical systems. What's your prediction? Will Flight 12 hit 100% of objectives and prove the faster moon path works? Drop your thoughts below. If this breakdown delivered value, hit that like button and share it with space enthusiasts who need to understand what's actually changing. Subscribe to Space Update 24 hours so you don't miss our coverage when Flight 12 launches. Thanks for watching.